So what we learned from the section was something that it was very hard to visualize from the full flow. What we learned is that what's important is transverse dynamics. We were whirling around, and that was pretty uninteresting. But what was going in the transverse direction, that was very interesting. So dynamics along the orbits, has some role, but it's not actually very important. And that's the real essence of Poincaré section. It isolates important stuff, which is how your neighbors go away from you or approach you, while you all march together along the flow, along your spaghetti, and that's less interesting. So that now means that we started with differential equations, Newton's equations or Rosler's or Lorentz or somebody's equations. And we have reduced them to a return map. See, we can compute this map for any point. So we start at point x1. Then we go from return time, tx, which is the first time we come back, which is, we did something and we ended up here at x2, and we compute the value of that function. So that's now a map. This is not a differential flow anymore, and obviously we can do it. So what used to be a periodic orbit which pierced the section 4 times in oriented way, now is just 4 points. And we think of the time in between as integer. If we ever need to return to the real problem, we will use the return time, which is the correct time for continuous flow. So now the problem is very much simplified. All this spaghetti structure is gone, and we're just seeing how the pieces of spaghetti are glued together. And how do we do that? Well, there is a simple way, which is if you look at this figure here and you look what happens at the end, you realize that every point that was here after one return is someplace else. So what you can do is you can construct a map of distance along this strange attractor, as it turns out, at time n. And on the vertical axis, we will draw the distance at time n+1, where I land after one return. That's called a return map. This return map is actually quite interesting. It's very simple. So it says if I started someplace at this end, so this is close to equilibrium point, which is unstable, then what happens after one iterate, I started at 4, I ended up at 6.5, let's say, which means I'm going away. So there's a whole bunch of points on the initial line which are close to the equilibrium, and they just get pushed away. Then there is a very important point called critical point, which is as far as I can reach. I cannot, I have no value higher than that. So this is the last point, and this point will be at the edge of the iteration at next time. And then here comes the thing that we saw. This whole interval here, this whole interval has a negative slope, which means that points which were further away are now closer and closer. So it means in meeting, we went like this, and then this half is now folded over. So things which were far, these guys here, far, they end up being very close after one iteration. So the operation is stretch and fold, stretch and fold. Now, this is not a particularly good Poincaré section. I just used the radial distance of the trajectory, the piercing. Poincaré section is 2-dimensional, not 1-dimensional. I will discuss how to do this better. And because it's not very good, this section, it can be weird. So we just show you a few examples. If I use B and C sections from before, this or that one to construct return map, I get something, but it's nonsensical. it is either kind of multi-valued and complicated. You see it's double valued in here. You know, if I have two values that initial point has, but that's not a function, or it's even worse in this case. So we will fix that, but you just get the main idea here.